assistant in our School of Computing and Information Science. Of course, Character Institute of Higher Education. His research interests are in deep learning, computer vision, and real-time object detection. And before I ask Ryan to make his presentation, I elaborate slightly the topic why we choose further explanation on object detection. The reason is that since RCNN and YOLO are actually very important concept in object recognition, but we did talk about that before, and therefore his presentation title is on further explanation. And one thing is that Ryan will slightly review the object recognition part, but we assume that the audience should still remember to some extent the previous discussion on RCNN or just object recognition by RCNN, something like that. And therefore, for the present presentation, could be a bit in-depth, right, discussion on both RCNN and YOLO, and which should be very useful to the whole team if you are interested in deep learning. Perhaps without ado, and I ask Ryan to make his presentation. Ryan.
Okay, can you hear me?
Yes, very
Okay.
well.
Okay, thank you, Professor Siu, for the introduction of this time presentation. So today my topic is going to have a further explanation and elaboration on the deep learning model, which are the faster RCNN and the YOLO. So today I'm going to go deep and talk about the details, and finally I will give a comparison of these two models and talk about their advantages, disadvantages, their characteristics, and so on. So first of all, let's have a very brief introduction on what is object detection. So since the start of the deep learning, the very popular model, which are the AlexNet and the LeanNet, are the network that do the object classification, which shown in the left hand side here. So it can tell what is the picture is telling. So here the picture have two bears, so the classification model will tell you it is a bear. And now we want to also know where is the object. So here it is a new topic called the localization. So we combine these two together, we will get something called object detection. We know the location of the object, and we can also tell what that object is. So that have some practical use of object detection, and first is the very common use, which is the self-driving. I guess you all have seen a lot more and more Tesla on the street, and Tesla, one of the feature of that car is that they have a very good self-driving system, and self-driving system require to recognize the car and the person on the street, so that the car can do the determination to avoid crashing on the obstacle. So the second use, which is become more and more popular since the pandemic, the COVID-19. So to measure the body temperature, we will use infrared camera, of course, but infrared camera, it can measure the whole area of the sensor. So how do we extract the information of that body and that person? So of course we use object detection again, and we use object detection to, oh no, here is a guy, so then I extract the area of the measurements of this area, so we know it's 36.3 degrees Celsius. So here is two very popular use. And let's talk about the first model, which is faster RCNN. So let's go through the basic structure first, and here is the look of the faster RCNN. So first of all, it will have a convolution layer which do the feature extraction. So the convolution layers, they will use a 3 by 3 kernel size is shown here. So it will have a padding, zero padding at the surrounding. So you can see there have a many zero at the outside of the box. So with the padding and the 3 by 3 size, the map size will not change. So, but here we will then use mass pooling 2 by 2 straight 2. So after mass pooling, the size will reduce it by half. So here is 4 by 4 input and will give 2 by 2 output. So second, it will do the region selection. After the convolution layer, it will extract a feature map. The feature map will go inside the region selection layer, which called the region proposal network. So it's look like this, and I will explain in further pages. So you just have a look first, and then finally it will go to classification. Of course, we want to know what is the object, what is the class of the object. So to further explain on the region proposal level, it look like this. So first of all, it will go through a 3 by 3 convolution, and then it will separate into 2 rows. So and the top row is, you can see the number is 1 by 1 by 80. So what does it mean? I will explain later. And the bottom is 1 by 1 by 36. So after something called 1 by 1 convolution, it will give 2 block. So one is 18 channel, one is 36 channels, but the purpose I will explain later. So then after the 1 by 1 convolution and extract the feature map, the top row will go through a softmax classifier, and the second row will just return back to something called proposal layer. And after the 2 rows, it will get the proposal, which is the binding boxes. Here I will ask you a question: what is this classifier for? So you can think about this first, and I also will reveal the answer later. So if we draw the 2 rows, the block out, it will look like this. The top one have 80 channels, so 1, 2, 3, 4, and so on. And the below also the same, 36 channels. So if we combine these 2 blocks together, we don't know yet what it is, but if we combine these 2 blocks together, and we can get some proposed binding spot look like this. So this is the selected area of the object. So of course we will go back to the image, so we can do classification. So to do the classification, something called ROI pooling is used, and since the classifier will require unified input, for example here n by m, so no matter the region you proposed, no matter it's small or big, it have to unify into same size, so that it can go to a softmax classifier, and then it will tell you it's a bear. So how to do it? So let's have an example here, which is a 5 by 4 map. Now we want a 3 by 3 output. So first of all, we do division. So 5 divided by 3, which is equal to 1.66, and we round off it and we get a 2. So here 2, 2, and the remaining, of course, will be the last group. So here is 1. So you can count is 1, 2, 3. So at the height, we do the same thing. 4 divided by 3, we got 1.33 round off into 1. So here 1, 1, and the remaining will be the last group. So the ROI pooling is meant to extract the same. We want to have a same output. So let's do a mass pooling in the grouped input. So it will look like this. Let's have a further explain on ROI pooling. So let's talk about what is the difference between ROI pooling and the traditional. A traditional mean is mass pool or FH pool. So let's look at the right side first. So the traditional pooling will want uniform space, which means the grid boxes will have the same size. Here the example is 2 by 2 with 2 stripes, so it will look like this, and you can see every single grid here is same size. But in ROI pooling, because we want a unified output, so no matter what is your method, you must give the same output and you must have the same grid. So here I give an example of 4 by 4 grid. So here I have a 6 by 5 input map. We want 4 by 4 output. So the first method I give is the most straightforward method, which we just write 1, 1, 1, 1 here. So and the remaining will be the last session. So and then you can get a 4 by 4 output. Here is the most simple but not accurate method. And the second I have I mentioned is to do the same thing as the last page I did. So 6 divided by 4, which is equal to 1.5. So 1.5 we round off, which is 2. So 1.5 we times 2, which is equal to 3. So here 1, 2, and 3. So 1, 2, 3 is here, sorry. So we have to divide it like this, and then 1.5 times 3, which is one off, which is 5. So here is the fifth one. So we divide it here. So same idea apply on the height. So we actually got a 4 by 4 grid look like this. So we can do mass pooling here, which is this 2, this 1, this 4, and so on. So here is the second example. So the concept of ROI pooling is to have a uniform grid, but not the size. So you have to decide it to grid with uniform. The size here is 4 by 4, so you can design your own one. So we now have gone through the structure of the network, the faster RCNN. So let's see how it locates object by using something called anchors. So anchor is a preset boxes. So it is multi-scale and multi-size and is fixed. So that's why it called anchors. So the multi-scale and the multi-size will bring it more suitable for various object size and shape. So anchors are created on every point on the feature map, which look like the below link. So here after the convolution layer, it will have a feature map, and each feature map in each point it will contain 9 anchors. So 9 is the most common numbers of anchor set in the network. So just assume it's 9. Actually, it can change. So every point in feature map include 9 anchor boxes. So if we project back to the image, it should look like the green boxes in the right hand side. So the green boxes in the right hand side here. So as you can see, the original image was gripped, which divided into many boxes. So why do the feature map withdraw the anchors on feature map? Why it will go back to original image will be gripped? So this is another question, and I will talk about it in the YOLO session. So here now we have we create some anchors on every point on the feature map. So if we draw it out at the same time, it will look like the left hand side here, which look very complicated, have a tons of boxes here. But on the original image, it doesn't have as much object as here is showed. So how do we select some of the boxes out and do the final modification and let it fit the object? So how do we do it? So first we want to choose the anchors. So choose the anchor means we want object, and it brings us to the also probability problem. So here at the first page, second page, I asked what is the classifier for. So here we review the answer is for the probability. So the probability of the boxes of the object or the background. So here we have two classes, and because we have line anchors as we discussed, so 2 multiplied by line, which is equal to 18. So this is how the 18 channels come. So second, we want to modify the size and the position of the anchor boxes to fit a real object box. So because we are on the two-dimensional map, so size we will have to multiply by some scale, and the position we also move by some distance. So we have 4 class here, 4 section here. So 4 multiplied by line will be equal to 36 channels. So this is how the 36 and the 18 channels come. The 18 channels is for the probability. The 36 channel is for the offsets. The offsets mean the final modification. So if we draw the these two block out, which channel we can see the first channel will be representing the anchor 1 object, and the second will be anchor 1 background, and so on and so on. So same idea on the 36 channel. So X shift, Y shift, X scale, Y scale. So here is the here is to draw it out, so you can have a more clear image on what is these two boxes. So to turn the anchors into actual binding boxes, I will introduce something called a 1-by-1 convolution, which I already mentioned. So how do we propose the probability and the offset for the anchors by just a feature map? So we will use a 1-by-1 convolution. So here feature map, and in previous slides I have talked about it will have some preset anchors. So here is a jump connection. But now we do 1-by-1 convolution using the same map here. So it will get 80 channels and the 36 channel. So with these two block, the information they carry plus the preset anchors, and we make use of the information of it, so we can actually to label, or we have some binding boxes of the object coming out. I don't know if you can watch it. Yes, here I enlarge the slide so you can watch it more carefully, more clearly. So yeah, the red boxes are the changes modified anchors, so it can now locate the object. So here have some extra questions. So first of all, what is the reason we are using the anchors? Well, we can just predict a new box directly. So anchors, anchors are fixed at multi-size and multi-scale, so which means it fit most object shape. Second, since anchors are already covered in most area and most shape, and I don't know if you have studied the WestLab before, but all in all, WestLab is to find the difference between input and output, so it can easier to train. So here anchors is the same idea. I assume this red dot boxes is the actual object location, and the blue is the anchors we set. So we can see that the closest one are actually quite close to the real object. So we can just force the lab will just need to learn the difference between the anchors and the real object, which is the same idea of the WestLab. So by setting anchors, it is making the whole system more easier to change. So here is why we use anchors. So Then the second question is that why do we separate object and backgrounds at two sections for the softmax classifier? So here you can see each have 7 times 7 times 9 times 2, which means it's separate into two classes or two sections for the softmax. So why does it? So let's see this example here, this two bear again. So look at the small bear, and we have a yellow anchor and the purple anchors here. So let's look for the yellow anchors first. So if I ask did the yellow boxes include an object, I think sure the answer will be yes. So let's give it a score of 0.7. But then I ask you a question again, which is, should the yellow box consider as background, since it seems like it contains more background than the object? So yes, of course I will answer yes again. Then the score I give him 0.85. So if we don't calculate the background score, we just use this one by the equation of 1 minus object score, which is equal to background. Then what will we get? A 0.3. But we want to remove it. So 0.3 are not enough score for we to remove these yellow anchors. So let's look at the purple one. So for this object score, of course, is high enough. For background, it's also low enough. So the network will keep these purple anchors. So here is why we separate into two classes, because we want to remove the anchors that include object, but mostly is background. So we have introduced the basic structure, the ideas of anchors, but we have still not discussed why does the anchors work. Why does it work to find the object? So in the following pages, I will give my answer of why they can find the object and they can locate at it. So let's bring through some very basic and fundamental idea of the deep neural network. So at deep neural network, especially when the size is reduces, so we call it an encoder. And one neuron of the deeper layers actually represent all information of the whole original signal. It can represent all of it. So if we look back in the FastTar RCNN model, after the convolution layers, the size is downsized. So the convolution layers actually have compress the feature into the region proposal network. So therefore, I will say that in the convolution layers is already extracting or condensing the features in the area of the anchors. By what? By heavily training. Because we train it like this, we label the sample data into we label it with our desired format, so that we can, by using heavy training, we can force the network to extract the anchors so that it can be for the further one by one convolution to know their properties. So here is a very key work is heavy training. So this is very key. This is very important. So then let's look at the one by one convolution. We now know that the convolution layers will brings the feature of the anchors in together. But how does the one by one convolution turn the feature of the anchors into some information like probability or the offset? So if you don't know one by one convolution, you can just look at the mathematical explanation here. But mathematical explanation is for when you are designing the level, which does not the topic of today. So let's don't look at this mathematical explanation. Let's look at the graphical looking. So here I have let's say 512 channels again. So with a same pixel, but in all channel, this one pixel, but in all channels. Let's multiply another 512 one by one chunk. Here is one, but have 512 channels. So we multiply it and we sum up the channel into one. So now we have a blue one here, which is a one channel. So now if we want to add another channel into the output, we just add one more chunk here. So the advantage of this is we can modify the channel size freely. We just add more and more block, and then we can get more and more channel at the output. So second, because this one by one convolution, this stick is also contains weights, the parameters. So it is actually trainable. We can train this one by one map, one by one kernel. So it is trainable, which means depends on our training sample. They can perform in different usage. So first usage is to in FastStar CNN is combine the features and to becomes the properties, and yeah, because it's trainable, so it can actually turn the feature into properties of the anchors. So here, so I know you may have been some confusing of what I'm talking about. So here is the final conclusion of how does the FastStar LCN work. First of all, we have some anchors which we are set in the RPN, but because of training, actually in the convolution layer, it already concentrating into same pixel, but of course in multiple channels. So it is actually the convolution layer is extracting the features of these anchors which we are set. Then it will go to a region proposal network. The region proposal network will do one by one convolution, and we have two rows. The first row will be the active channels one, which will give the probability of that anchor does it contain an object. So the second is to do the offsets, which mean we modify the anchor so it can fit the object position and size. So if you combine these two information into this one, which mean on every feature map, on every pixel on the feature map, we create 9 anchors. It look like this. So if we combine these two together, and we can select and modify the anchors so that we can propose some bounding boxes. So the bounding box will go back to the original image or original feature map, so it can do the further classification. So this is how the FastStar RCNN work. So let's talk about how do we choose the boxes. We have talked about how do we extract the probability, the offset, the information, but how do we really choose from it? By using the probability we calculate. So first of all, let's introduce an IOU. And an IOU is, in full name, is intersection over unions, which means the overlap divided the union z, which means is n divided by all. So here let's look for the example. Here it have two boxes, so it's overlapped 0.25 of each of them. So if we calculate it, it's equal to 0.143. So here is another example. We overlap 0.66, which means 2/3. So if we calculate it, it will equal to 0.5. So here you can see the bigger the IOU, which means the more the overlapped area of two bosses is. So one IOU, which means it's totally equal to the ground truth. The two bosses are identical. So the second concept we have bring is called law maximum suppression. So every anchors and is okay. Don't look at the words. Look at here the example here. So first we choose the bosses with higher probability after we classify it. So here is 0.94. So of course it will have some surrounding bosses which is have similar probability with it, but because it's higher we choose it first. So when another bosses have, let's say, 0.7 IOU with it, which means it's overlapped the most area of it, so we will remove it. We will remove the lowest one. So that's how we get the only best result. Let's say we have another box here, 0.93 probability. So because it have a smaller IOU, which is smaller than 0.7 with it, so we actually determine it as another object. Of course, in reality, two objects may be overlapped together, so we don't want to remove all of them. So we have to set a threshold here to keep the close, but actually it is another object. So law maximum suppression is to choose the best from many. So now we go don't scared by the code first. So I have summarized it from it. So in the training session, so of course we don't want to only choose the best to calculate the loss, is not efficient. So we just separate them into groups for calculating loss. So first, to save the anchors which have interact with the ground truth. So let's just save positive for the anchor which contain ground truth first. Then we will save 0, which means a negative sample for background. If the IOU, the anchors have IOU 0 lesser than 0.3 with the ground truth, we set it as negative sample. So third, we save -1, which means we don't use it if the IOU is between 0.7 and 0.3. So because there are a lot of anchors will have intermediate score, but the effectiveness or the effects of them are not big enough. So for saving time and efficiency, we do not use it for training. So if we look at the example again, first we will remove, of course, the boxes outside the image. So then the threshold of IOU larger than 0.7 we will consider as positive sample, which is the purple one here. The blue one is actually the ground truth. And lesser than 0.3 we will set as negative sample. So here yellow maybe is less than 0.3, so we set it as background to train. So the other boxes, no matter no matter where it is, but if its IOU is between 0.3 and 0.7, we do not use this for calculate the losses. So here is how we separate the groups of the anchors into positive and negative and useless sample. So then we will talk about evaluation or testing. So we will first rank it and extract the top n bosses for further choosing, because we want to have more efficiency. So we just choose the top n for efficiency, and then go inside the loop. We will first remove the small bosses, but why, I will explain. And then we will remove low score bosses. Of course, we want to keep eliminate the low probability bosses for efficiency. And then we'll finally do the long maximum suppression I've talked about. So the only one object will have one bosses. So look at the example again, and let's choosing the top end cluster. We will remove small boss, remove low probability boss, we long maximum suppression so that we can remove the unwanted or extra bounding bosses. So why do we remove small bosses? So here I give two reasons. The first reason, which I actually quite disagree about, I disagree myself. So, which is if there is two bosses here, one is particular smaller, so the IOU of it is quite small. So, non-maximum suppression cannot kill it. But then actually I think about it, and the blue one actually can be another object. You eliminate the another object which is not make sense and reasonable. So but the more make sense reason is that to prevent a boss which is smaller than the ROI pooling required. If you can remember, the classifier require a unified input. So let's say the classifier need 10 by 10 inputs. Now your bosses is below 10 by 10, and you cannot do ROI pooling with it, and it will just make the program crash or error. So for convenience, we remove the bosses smaller than the classifier required. So here is the more suitable reason. And finally, let's have a conclusion and talk about the performance of fast-style NCNN after we talk about like 30 minutes. So first of all, it have feature extraction of the anchors, so in the convolution layer. So second, we will use the feature map, and we will choose the proposal, which means the bounding box from it, and combine the bounding box and the original feature map. We will get and we will extract or cut out the region and do ROI pooling, then for classifier to classify what it is. So let's see here the precision. Fast-style get a quite high precision. So but the runtime is not ideal enough for real-time applications, since it have around 0.2 second per frame, which if we calculate is just around 5 FPS, not really close to real-time. It have a very long way to go actually. So what is real-time is mean is at least it have 25 or 24 FPS, because the film are also shooting at 24 or 25. So it have a long way to go. But now let's talk about another model, which is YOLO. You only look once, which is popular or famous because of its fast processing. So in their testing on the Titan X GPU, the YOLO have about 45 FPS processing speed, which is quite fast. So it is actually something called a region-based or a one-state method. So what does it mean? Fast-style CNN, as we talk, it is a two-state model. So which two-state? Let me draw it out. So here we have feature map here, but then we separate into two rows. One is for the proposal, and the another we will go back for the classifier. So we call this as two-stage because it's do the things twice. But YOLO is actually something called one stage because it just has one forward done. So that's why it can be so fast. But let's look how the YOLO work with just one stage. So the main idea is at the output. I don't know if you can see the numbers of it, but it's actually 7 times 7 times 30. So the concept of YOLO is mainly rely on this output size. So 7 by 7, what does it mean? 7 by 7 as we have talked about the fast CNN, I have shown you this image. You can see the extracted or downsided feature map. If we project it back to original image, it will look like a gripped image. So let's see a very simple example of the left hand side here. We have a 4x4 map, and we come through and pulling. Now the size is halved. So the top left 4 actually is condensed into 1. So it can actually representing the top left 4 again. Here I identify it by color. So same idea of the white bottom right one here. It can represent the 4 here again. So actually 7x7 mean we grip the image into 7x7 boxes. So it look like this here. But how about the 30 channels? So again, I have talked about 18 channels in the facile CNN section. So it contains the probability of the anchors. So what does it mean in YOLO again? So actually 4 of it we are representing the position and the size of the boxes. And one of them is something called confidence. Actually is probability. And in each point it will have 2 boxes. So this 7x7 grip, which in total 49 points, each of them will have 2 boxes. So for each point it will identifying 20 classes in one hot code, which look like this. Therefore the number of channel is equal to 4, which is the bounding box information, and 1 for the confidence, and 2 for the boxes. So we multiply by 2, and because each point is representing 20 classes, so we plus 20 here, but not inside this bracket, because we are talking about points doing this job, not the boss doing this job, not the boss but the point. So each point only can detect for 1 object only. So yeah, it's a very clever design that make the network output look like this. So, and with the proper labeling sample, we can train it to do the object detection. So so let's have a very little conclusion here. So the YOLO, I have shown you the network, which is very simple. So the at the beginning part, it is convolution and pooling again. So it's actually doing the feature extracting. Of course, if you know about CNN, you will know the convolution are doing feature extraction. So meanwhile, it is actually decreasing the size to 7x7, and then the fully connection layer is introduced. So it actually can resize the input into 30 channel. So here the input is 1024 channels, but the output is 30. So the fully connection layer here is to modify the channel size, so it can turn the image feature into properties we have just talked about. So let's talk about the loss function of the YOLO, which is quite interesting. So it's a simple square root loss function, and let's explain it one by one. So first of all, the label, let's say it's something here first. So this something, what does it mean? The OBJ or stand for object, which means if will be 1 if the boxes are included like ground truth, 0 otherwise, of course. And the NOOBJ, which stand for no object, will be equal to 1 when there's no ground truth, 0 otherwise. So for example, for the boxes that include a ground truth, because we only have low object at the 4th item, so we remove 4th item. So the log function will only have 1, 2, 3, 4 item. So for the bounding box that doesn't, so it will be revised or opposite. So it will only have the 4th section remaining. So the other one will be eliminated. So the first two items are actually quite easy to understand. So but here we look at, they have a lambda here, which actually is we increase the ratio. Why? Because the ground truth, the boxes include the ground truth are commonly lesser than the boxes doesn't include a ground truth. So we want to increase its ratio. So here we set it to 5. So here I have 2 boxes for example again. So you know why it's look like this. So it's a easy and very simple square root loss function. So I don't talk about it very details, just simple math. But that have something that we want to notice is here we have a square root on the second one. The second one, what is the second one do? It's actually calculating the size of the 2 boxes. So why do we do the square root? So let's have 2 different example here. So first one, we have 800 times 600. Let's say the output of the model, and 820 and 620 for the ground truth. So because it's only have 20 difference, and because it's so big, so you cannot really tell they have a very big, huge difference. However, if you look at this one, it's also the difference is 20, but this time is much smaller. So you can see that it actually quite different. So the usage of the square root is to make use of, or to minimize the loss of the big bounding boxes and enlarge the small bounding box. So you can see after the calculation, with the square root calculation, we will have a very significant improvement. Here is 4.5, 5.4, but here is only 0.28. If we don't include square root, it will be same 800, 800. So how can the system train the white one to be more precise? No. So therefore we add a square root to minimize their difference. So for confidence and class difference, how do we do it? So for confidence, if it is included a ground truth, which means it is equal to 1. So because probability, 1 mean the ground truth and 0 for no ground truth. So here for the bounding box include ground truth, we will set it to 1. For the one who doesn't include, we set it to 0. So here you can see another lambdas here, which this one is to lower the effect of the boxes that doesn't include ground truth. So we set it to 0.5 to avoid them. So the lastly, the classes loss function. Let's say we have 3 classes. We only determine 3 classes. So the ground truth is bear. So for cat, the system tail is 0.12. For dog, the system tail is 0.15, and the bear is 0.73. And because the ground truth is bear, so ground truth of bear is 1, and the other 2 is 0. So the loss function will be shown as follow. So 0.12 minus 0 square, so on, so on, so on. So it can actually calculate 0.1098, which is quite low because it's already tell the bear have the highest chance. So the losses will be small. Of course, it makes sense. So let's have a conclusion and performance discussion again. And because by using the output size, we modify the output size into 7 by 30, and with the data sample labeling, the network actually are trained to turn the image into probability, into bounding boxes, into classes. So here is a very clever design, I can say is very deep learning. So because of the simple convolutional neural network, it can process image into 45 fps. So as mentioned, for camera and video usually is run on 24 or 30 fps. So YOLO, it can have a real-time application now because it's larger than the basic or fundamental frame size and with acceptable precision. So let's have a comparison of these two models. So I have mentioned 2-stage, 1-stage. So what is the difference of 2-stage or 1-stage? So for 2-stage, it will use the image to extract the region, and use the region. We go back to the original image so that we can put it into a classifier to do classify. So because we make use the image again, so that is less losses on the image or feature lab. So with less losses, of course, it is more accurate to classify. So for 1-stage, it transfers image to class and location in just one convolutional neural network model. So here is an example. So we input an image. First, it is going down the size, or it is selecting a region. So with selecting the region, at the same time, it's also extracting the image or extracting the features. Yes, extracting the features. So here you can see it's quite deformed, or we can say it's lost, have some data loss while we are doing the region selecting and the feature extraction. That is some losses. So because of the losses, it's actually less accurate, but it can do it faster. So as I mentioned, 2-stage, because it is doing the region proposal and the classifier separately, so it will require longer processing time. And 1st-stage, because it's processing the object location and the feature extraction at the same time, there must be some information loss on the target, so it will have a lower precision. So let's have a side-by-side comparison on both model. So we can see here MAP, which is stand for mean average precision. So you can just think it about it is a precision score. So for the highest one is the FastStar SCNN with the convolution model VGG16. So it have a 73.2 precision score. However, the FastStar SCNN did not have very fast speed, so it cannot use on the real-time application. While the YOLO, you only look once, have a real-time processing speed. And in the real-time detector, YOLO have the highest score. So here is the two major performance difference of these two models. One have higher precision, one have higher precision in the real-time application. So there are some similarities of these two models. So you can make use of it for your further or your future object detection model design. So first of all is scripting. So both of them are using scripting by downsizing the original image. The feature map are downsized. So here the two models are also with downside the half every time because it's more easy to calculate. So then it will compress the information into let's say this area into only one pixel or one point. So it will compress the information of each area into one point. Second, it will have channels representing some properties. So for fast-style CNN, let's say the 80 channels again, the anchors or the channel which representing and score of object and background, score object background. So the YOLO which actually representing the bounding box position, the confidence, the second box, and the class. So it actually use channels to carry some property, the information of the bounding box. So IOU and long maximum suppression, which is quite common on object detection model because it can choose the best box from many. So of course these two models will have use of it. So however, in further version of YOLO, let's say YOLO V2 version 2, anchors and one-by-one convolution were used to enhance the performance, just like the fast-style CNN do. So which means the YOLO have learned something from the fast-style CNN. First is anchor, because anchors now it can learn the object position more easily. It can more easy to train the network, the model. So it make use of anchors. Second, it will have a one-by-one convolution rather than the fully connection layer. Now one-by-one convolution are easy to reduce the size and to extract the properties of it. But most importantly, or finally, the final conclusion, most importantly, the reason why of these two models work because they have training. They have heavily training. So because they are deep learning model, of course they have training. You may think I'm just saying some trash, but no, I want to keep mentioning that because of training, these two models can work. So please remember when the researcher designed the network, we just designed to do convolution, to do pooling, or to do softmax to classify. So, but the network are not doing feature extraction or the property or the information extraction. We did not decide this, but by the training, the system are moving to extract the feature and turning the feature into some properties. The position, or turning the image, which is just a pixel by pixel, into some property like position, like probability, or like the classes. So please be remember, we just only design the convolution or pooling or softmax, but with the training, the data sample, the labeling, so we can actually make it have a various use. So here, the two final example I want to mention is the first one is from fast-style CNN to extract the feature of the area of these anchors, these multiple anchors, into one pixel. Of course, multiple channels, don't forget about it. And the second example is to turn feature into something like location, class, and probability, which you cannot do it by just have some fixed rule or fixed code. We only use training to make the network do this like magic work. So my presentation here is over, is the end. So I'm welcome you to ask me any question about today's presentation. Oh, thank you.
Thank you, Ryan. Provide us an interesting talk. And perhaps I ask if any questions from the audience. Any questions? Anything you want to ask? Yeah, anything you want to ask Ryan? Now, am I right to say that, Ryan, besides training, actually the RCNN are still make use of certain external connection, external process or signal processing process to fulfill the requirement since it involves two stages. But for the YOLO, essentially, it just make use of just a single deep learning system to achieve all this. Am I right to say that?
For facile NCNN, I'm quite disagree about because facile CNN, there are two stages. The first stage is for the convolutional network, the backbone, the let's say VGG16, and the second stage is the region proposal network, which is using one by one convolution, which is also convolution and something to train again. But for the previous or the oldest RCNN, like the first RCNN and the fast RCNN, yes, it have used some external method like the area selection, which called is something traditional signal processing technique. So for the old one, yes, but for fast RCNN, I would say it is no. So
it's already become deep learning oriented. It's
yes,
not involve other techniques.
yes,
But the conceptually still the same. Am I right?
yeah, yes,
Yeah, conceptually it's still the same since just like you make use of those processing technique to make the explanation. But what you said, due to the training such that we can achieve this. But one thing which is important, you said already, is due to the loss function.
yes. Loss function design is also important.
Or otherwise we won't achieve as what we want.
Yes,
Am
yes,
I right?
yes.
This is very important, right? And since the especially the loss function design, and you talk about it in some details, but in the future I would expect more of the presentation talk more on the loss function design, since these are the important issue, force the system to obey what actually our theory is. And furthermore, it is very time consuming, but to wait for these various losses to put on the system such that the training can be done or can be done easily is another very important issue.
Yes.
Am I right?
Yes.
Yeah, from your experience. All right. Now, before we adjourn the meeting, may I ask any more questions? Any more questions? Right? And especially if Professor Chen is still on the system, any comment from Professor Chen, or he is on another meeting? Yes? All right, he may be on another meeting. Right? Yeah. Any questions from others? If no, then we adjourn the meeting. And but I must say that never mind to talk topics which we presented before. And since what we are talking about are some very complicated system, and in such a way that the more angle of view from any of you would be welcome. And therefore, for any of these